Hi, my name is Harry Chernoff. I'm a professor of operations management at NYU Stern. I'd like to introduce the concept of project management, a technique used to help managers manage one of the most common and interesting types of processes that we deal with. Initially, we defined 5 different categories of processes: continuous flow, lines, batch, job shops, and projects. Projects are at the end of the continuum, have the least amount of repetitive flow, often having only 1 unit of output per project. Projects are depicted by network diagrams with arrows and nodes denoting the tasks that comprise the project. Because they're quite different from other types of processes, projects have their own set of analytical techniques. These techniques can be applied by hand or by using available software. There are 3 tiers to the concept of managing projects with these techniques. First, critical path methods. Drawing a network, identifying a critical path, and determining the duration of a project. Once we know the duration of the project, the question becomes, is that duration acceptable? Often we've promised a delivery date that's sooner than the project duration that we calculate. In that case, we need to reduce the project duration, a technique we refer to as crashing the network. We examine the cost of reducing 1 unit of time, say 1 week, of each of the activities on the critical path, and select the least expensive way of reducing that path and hence reducing the entire project duration. One of the problems with project management techniques is that in real life, the durations are not deterministic or constant. To include the reality of changing task or activity durations, we use a technique referred to as PERT, Program Evaluation and Review Techniques. This technique allows us to input a probability distribution on each activity duration and utilize that distribution in determining how long the project will actually take to be completed. With probabilistic durations on each activity, our project duration is no longer deterministic. It also is a probability distribution. And our final results, instead of saying a project is finished in X weeks, is to say the probability that the project will be completed in less than 3 weeks is equal to 85% or whatever solution we have. Our projects are made up of interrelated activities that are associated to each other with precedence relationships. Each activity or task might have activities that are completed before it can start and activities that must follow. These precedence relationships are most commonly shown in a network of arrows and nodes. The activity name can be shown in a node. Let's take a look at an example. Let's say we want to draw a project that has 4 activities, A, B, C, and D. The precedence relationships are that A is completed first, then when A is completed, B and C can begin. D can begin after both B and C are completed. The activities are drawn in nodes and can be connected in a network diagram. Here we see the 4 activities A, B, C, and D. The entire project has 2 paths, A, B, D, and A, C, D. By putting the durations of each activity onto the network, we can see that the 2 paths have durations of 8 weeks and 9 weeks. The longest path determines the duration of the project. It's called the critical path. The activities on the critical path are critical activities. And they're critical in the sense that if they're delayed, the project will be delayed. Activities not on a critical path are said to have slack. They can be delayed or started late without affecting the project duration. Durations are given, observed, or derived from past experience and data. Durations can be constant or variable. When we wish to reduce the duration of a project, we can crash the network. This involves spending resources, usually money, to get activities done in less time. Each activity is examined, and the cost of reducing it by 1 unit of time, say a week, is determined. Crashing is only done on critical activities. Crashing a non-critical activity will not affect the project duration. Often there are delay penalties associated with the project. For example, we pay a penalty of $5,000 a week if the project's not finished on time. If the project is coming in late, we want to compare the cost of crashing to the delay penalty and make a decision. Optimally crashing a project means finding the optimal or minimum cost duration of the project. In our example, with 4 activities, A, B, C, and D, assume we have costs associated with reducing each one of those activities by 1 week, as shown, $2,500, $2,000, $1,000, and D is unable to be reduced. We could consider this to be an extremely high cost. We see that C is the cheapest way to reduce the project duration in the critical path, ACD. If we reduce it by 1 week, we'll spend $1,000, but we'll save $5,000 in the delay penalty. So our net saving is going to be $4,000. What's the critical path now? Well, as we look at the diagram, we can see that both the 2 paths now have durations of 8 weeks. So there are 2 critical paths, and the project duration is at 8 weeks. What if we needed to reduce the project by another week? To do this, we'll have to reduce each of the 2 paths by 1 week. We can do this by crashing an activity that's common to both paths, or by reducing a combination of activities, one that's on the first path and one on the other, in our example, possibly B and C. We can see with the costs involved that reducing activity A would be a less expensive way of doing this. Let's take a look at a situation where our activities are not constant but are variables. Often we get these variable times by asking the contractors or managers that are running these activities to tell us what they think the most optimistic, shortest time period will be, pessimistic, and most likely duration of the activity. In this way, we get a distribution of times that we can use for each one of the activities on our network. The method of PERT analysis makes an assumption that these distributions are 3 estimate distributions. They have a low time, a pessimistic or high time, and a most likely time. For each of the activities, we can calculate the mean of the activity duration and its variance by using the PERT formulas. When we have the mean and variance of each activity on the network, we can then find the project duration by looking at the critical path and adding the means of each activity on the critical path and adding the variances along the critical path. This gives us the mean of the project duration and the variance of the project duration. If our activities were 3 estimate activities, then we can assume that the project duration will be normally distributed. This is one of the important aspects of the PERT method. By knowing the mean and variance of a normal distribution, we can, through normal analysis, calculate the z-statistic and, using a table, determine probabilities of the project taking various amounts of time.